Lesson 3, Unit 11, Buffers. We'll be looking at what is a buffer, buffer capacity, and calculating buffer pH using pH equals pKa plus log A minus over HA. Buffer solutions are based on weak acid or weak base conjugate pairs. A buffered solution resists changes in pH when small amounts of acid or base are added. We do this by using a conjugate acid-base pair of weak acids or weak bases to form a buffer solution when both acid and base are present in significant quantities. So you need the conjugate acid-base pair, and you need to have the ratio ideally be 1 to 1 so that you can consume as much acid as you consume base. But in reality, you want to choose somewhere between a 1 to 10 ratio and a 10 to 1 ratio of the conjugate acid to the conjugate base. So let's take a look at an example using acetic acid and sodium acetate. And if we have a mixture of this, look at how these two resist a change in pH. So remember, our acidic hydrogen for the carboxylic acids is this terminal hydrogen. Here's our acid. If we add base to the solution, because we're adding, this would be a strong base, it's going to go 100% to completion. So what happens is the acetic acid mops up the base. Now, if instead we decide that we're going to add acid to this solution, now the acetate component can react with the acid. The reaction will go 100% to completion, and we can see that the acetate ion will mop up the acid. So the pH will not change significantly as long as we have conjugate acid or conjugate base to mop up one or the other species. So we have to have a conjugate acid, conjugate base pair. So let's take a look at two different pairs. Here's the ammonium chloride ammonia pair. The two reactions that would take place is the ammonium ion would react with hydroxide ion to form 100% H2O plus NH3. The ammonia portion, NH3, will react with any added hydronium to produce NH4 plus the ammonium ion and H2O. Another example would be H2PO4 minus and HPO42 minus. This is our acid. This is our conjugate base. So we would have H2PO4 minus would react with any strong base that is added to form HPO42 minus plus H2O. And the HPO42 minus will react with hydronium ion to form H2PO4 minus plus H2O. So it's important here that you have the conjugate acid-base pair. So let's look why the following pairs would not form a buffer system. So these are non-examples. In the case of HCl and NaCl, HCl is a strong acid. It's not a weak acid, and we need a weak acid. In the case of acetic acid and NH3, this is a weak acid. This is your ammonia ion. Okay, so back here, sorry about that. This is your acetic acid, this is ammonia, this is a weak acid, this is a weak base. But the problem is that they are not a conjugate acid-base pair. So this will not work as a buffer system. So it's not a conjugate acid-base pair. Our last set is HCl and ammonium chloride, and in this case they're both acids. So we need to have a base present to react with any base that we're at, or any acid that we're adding, and we don't have anything in this case. Okay, the last thing that we're going to look at is buffer capacity in terms of characteristics of a buffer. So the buffer capacity is the buffer's ability to react with any extra acid or base that is added. The higher the concentration of the buffer components, the more acid or base it can absorb. So we can't see the reactions above. I've rewritten them down up here. So the more we have, the higher its capacity. So if we have more ammonium ion, it can react with more hydroxide. If we have more ammonia, it can react with more hydronium ion. So for example, if we have a buffer solution that is 0.1 molar in both the weak acid and its conjugate base, we can absorb 10 times as much acid or base than if we only have 0.1 molar and 0.1 molar in the same volume. Now, ideally, we want a 1-to-1 ratio of A- to HA, so we can mop up the same amount of acid and base. Okay, let's look at calculating buffer pH. So a buffer solution pH is really determined by the pKa or pKb of the weak acid or the base and the concentration ratio of each component. You can use the Henderson-Hasselbalch equation here, and this is on the AP sheet, to calculate the buffer pH. This is a great equation. If you want to, you can continue to use ice tables and use the equations for Ka and Kb, but this is very convenient once you get used to it. Notice that what controls the pH is the value of pKa and the ratio of A- to HA. So as long as this ratio remains constant, your pH is going to remain constant. This means that you can dilute a solution and the pH remains unchanged because the ratios remain unchanged. So, the pH of a buffer will not change if the conjugate pair ratio is constant. The pH of a solution with 0.4 moles of ammonium chloride and 8.8 moles of ammonia in 1 liter will be the same as if we have 4 moles and 8 moles. The ratio remains the same at 1 to 2, but the more concentrated buffer solution has more capacity to absorb more added base or acid. So, why are buffer solutions important? Well, biological buffer systems maintain our bodies within a very narrow pH range. We have 2 key biological buffer systems that maintain our body at close to neutral conditions, and they are shown here, along with their respective values of Ka. Now, the reason I show this is really because this equation up here uses the pKa term. So, to refresh your memory, the way we find pKa is we take the negative log of Ka. And that's all there is to it. So, the pKa of the first one is 7.206. A little review on significant figures. We have 3 significant figures here, 3 significant figures. 2 significant figures here, so when we go to calculate the pKa, we would use 6.10. Same rules as we use for pKa. pH. All right, so let's calculate the pH of a buffer solution. We've got 2 liters containing 1.2 moles of H2PO4 and 1 mole of HPO4 minus. We're given a Ka value. So first, just for funsies, let's calculate the pH using the Rice approach, okay? So here we go. Let's do that. All right, so I've got the ICE table set up, and first off, let's make sure that we identify HA and A minus. So this is our HA, and here's our A minus. And since these depend on molarity, we're going to have to figure out the molarity of each of the solutions. So for HA, our molarity is equal to 1.2 moles over 2 liters, which is 0.60 molar. All right. And for the A minus, we have 1.0 moles over 2 liters, which is going to be equal to 0.50 molar. So we put those values in. We have 0.60, 0.50. Initially, we have none of the hydrogen ion concentration. We're going to be adding hydrogen ion, losing our reactant. We'll have 0.60 minus X, 0.50 plus X, and X. We're going to assume that X is very small. Really should write that down. So we're going to have 0.50 and X in the numerator and 0.60. X is going to be equal to our hydrogen ion concentration, which is equal to 7.48 times 10 to the negative 8th. Therefore, our pH is going to be 7.13. I only have 2 significant figures because I'm going back to my original data. Okay, so let's try instead using the Henderson-Hasselbalch equation. So we have 2 liters with 1.2 moles. Let me fix that. 1.2 moles of the H2PO4 and 1 mole of the HPO4 minus. We have our Ka equaling 6.23 times 10 to the negative 8th. So we need to figure out our pKa. pKa is going to be equal to 7.206. Okay, so I did that just by taking the log of the Ka value. pH is going to be equal to 7.206 plus log. And we just need to use a ratio, and so we can use mole of A over mole of HA. So mole of A minus over mole of HA. And so that is going to be equal to 7.206 plus log 1.0 over 1. 7.206 plus log 1 over 1.2 is 7.13. Notice that's the same answer as we got above.